Usually when we think of human communication, there's this expectation of, well, effortlessness. It's basically like breathing.
Right. It feels completely natural because it's deeply biological. I mean, our brains are hardwired for it from birth.
Yeah, exactly. You have a thought in your head, you move your mouth, an invisible wave of sound comes out, and someone else just effortlessly catches that wave and understands it.
A toddler playing with blocks, masters the fundamentals of language without ever reading a manual or studying grammar.
Or looking at a frequency chart, it's entirely invisible and incredibly fluid, but then you try to teach a machine to do that exact same thing.
Oh, yeah.
You try to get a computer to take that invisible, messy, fluid wave of sound and actually comprehend it, and suddenly you realize that what we do every single day without thinking is actually, it's a mathematical miracle.
It really is. Taking a machine and forcing it to listen puts you into a technological landscape that is incredibly murky. It is the absolute definition of computational muddy waters.
Because human speech is chaotic.
Pure chaos.
Which brings us to today's deep dive. We are cracking open a massive stack of research to figure out how we actually taught machines to capture that invisible wave.
And it is a long, surprisingly complex journey.
Right. Our mission today is to explore that journey. We're going to unpack how this technology evolved from clunky room-sized machines in the 1950s to the invisible AI sitting in your pocket right now.
And we'll break down the massive mathematical hurdles researchers had to overcome.
Yeah, and explore why this tech is both a profound accessibility tool and a very real, very surprising security vulnerability in your daily life. It's just a massive, sprawling story.
It is. But before we jump into the timeline, there's a crucial distinction we need to establish right up front to make sense of the research.
Okay, lay it on me.
People often use the terms interchangeably in casual conversation, but voice recognition and speech recognition are two entirely different computational tasks.
Wait, really? I definitely just use them interchangeably.
Most people do, but voice recognition or speaker identification is about figuring out who you are. It's using the unique acoustic properties of your vocal tract, like a biological fingerprint. Speech recognition, which is our focus today, is about figuring out what you are saying, regardless of who is saying it.
Which, as the source material makes glaringly obvious, is a monumentally harder problem.
Well, exponentially harder.
So let's rewind the clock to see where this all started. We are going way back long before the era of modern AI into the early 1950s. Teaching machines to listen is not a new concept at all.
No, not at all.
In 1952, researchers at Bell Labs built a system named Audrey. Audrey could recognize spoken digits 0 through 9, but there was a massive catch.
It only really worked for a single speaker.
Right. The notes mention Audrey was basically locating patterns called formants in the power spectrum of a specific voice. What does that actually mean, in plain English?
Think about how sound is physically produced. Your vocal cords buzz, and that raw sound travels up through your throat, mouth, and nasal cavity.
Right, the anatomy.
Yeah, and those cavities act as acoustic filters. They amplify certain frequencies and dampen others. Those amplified frequencies are called formants.
Okay, got it.
So Audrey worked by analyzing a power spectrum, which is essentially a graph showing which frequencies in the sound wave have the most energy or power at any given moment. The machine was hardwired to look for the specific formant peaks of the lead researcher's voice.
So, to use an analogy, it's kind of like an acoustic guitar.
Okay, yeah.
The strings create the raw vibration, but it's the hollow wooden body of the guitar that actually shapes the sound into something we recognize.
Exactly.
So Audrey wasn't really understanding the word 5, it was just recognizing the unique acoustic resonance of one specific guy's wooden guitar body when he said the word 5.
That is a perfect way to visualize it.
Is it?
Audrey was recognizing the instrument, not the music.
Wow, okay.
And a decade later, IBM took that a step further. In 1962, they debuted their shoebox machine at the World Fair. It's considered an absolute marvel of engineering at the time, doing addition and subtraction via voice, but
it still only possessed a tiny 16-word vocabulary.
right, just 16 words.
Because recognizing single, isolated words, especially from a person the machine is already calibrated to, is one thing. But human conversation simply doesn't work like that.
No, it flows. Words bleed into each other. The end of one word becomes the start of the next.
Getting machines to understand continuous sentences was the real wall researchers hit.
And that wall held strong until the late 1960s at Stanford University. A graduate student named Raj Reddy achieved something groundbreaking. He cracked the code on continuous speech recognition.
Because up until Reddy's work, if you wanted a computer to transcribe what you were saying, you had to speak with these artificial, unnatural gaps.
You had to talk like a stilted robotic movie alien.
Exactly, like, take me, too, your leader.
Yeah, you had to physically stop the sound wave so the computer knew where one word ended and the next began.
So what Reddy did was allow the audio to flow to the point where a user could actually issue spoken commands in real time to play a game of chess against the computer.
Which was huge.
It feels revolutionary because it fundamentally changes the human-computer dynamic from a data entry task into an actual interaction.
It shifted the paradigm entirely. But to fully contextualize this, even with Reddy's breakthrough in continuous speech, a massive puzzle remained completely unsolved.
The speaker independence issue.
Exactly. The chess system worked beautifully, but mostly for the programmer who built it. Building a machine that could understand anyone's voice, with all our different pitches, local accents, and bizarre vocal quirks, was still considered nearly impossible.
Right, because if everyone speaks at wildly different speeds, how did a 1970s computer not just completely fail the second someone drew out a word with a heavy southern drawl?
It usually did fail.
Or if someone chattered away like they just had 6 shots of espresso, the timing of the sound wave would be completely different from the computer's template.
And the solution to that actually came from Soviet researchers who invented a mathematical algorithm called dynamic time warping, or DTW.
Dynamic time warping. Sounds like sci-fi.
It really does.
Yeah.
But the logic behind DTW is brilliant in its simplicity. If the computer holds a perfect half-second template of the word hello, and someone with a drawl says hello over 2 full seconds.
Standard comparison fails because the peaks and valleys of the sound waves don't line up in time.
Exactly. So DTW mathematically stretches, or warps, the shorter sequence to match the longer one. It bends the timeline non-linearly, so the machine can overlay the actual acoustic patterns and recognize the similarity despite the completely different speaking speeds.
Okay, dynamic time warping is a great trick. But the sources show that the real paradigm shift, like the moment modern speech recognition was truly born, happened when researchers decided to stop trying to perfectly emulate the human brain.
Right, they abandoned the biological approach.
Yeah, or map individual words and instead just threw pure hard statistics at the problem. Enter hidden Markov models, or HMMs.
In the 1970s, researchers like James and Janet Baker at Carnegie Mellon, and later Fred Jelinek's team at IBM, brought hidden Markov models into the acoustic world. An HMM fundamentally treats a speech signal as a short-time stationary process.
Okay, I want to make sure we picture this correctly because this mechanism is the foundation for everything that follows. Think of a human running.
Okay.
If you just watch them run, it's a fluid, continuous blur of motion. It's incredibly hard to analyze every single muscle movement in real time.
Sure.
But if you film them and then chop that film down into a flipbook of tiny frozen snapshots, suddenly you can study the exact mechanics of their stride.
That's a great analogy. That's exactly what HMMs do to sound. They slice an acoustic continuous sound wave into tiny, rigid, 10-millisecond frames.
10 milliseconds.
Yeah, microscopic. In that 10-millisecond slice, the sound wave isn't flowing anymore. It's mathematically frozen. It is stationary.
And once you have those frozen slices.
The HMM uses pure probability. It looks at the acoustic data in that single frame and calculates the statistical likelihood of what phoneme, the smallest basic unit of sound, like the K sound in cat, is occurring in that exact fraction of a second.
Okay.
Then it looks at the next frame and the next, stringing those probabilities together to guess the sequence of sounds and eventually the word.
The historical context around this is wild, by the way. The linguistics community absolutely hated this approach. There was massive academic drama.
Oh, the linguists were furious.
Yeah.
At the time, this purely statistical approach was viewed as almost insulting to human intelligence.
How so?
Well, linguists argued that HMMs were far too simplistic to account for the true, nuanced complexities of language. Human language is built on syntax, semantics, deep structural rules mean...
And HMMs completely ignored all of that.
Completely. They didn't care about the definition of a word. They only cared about the statistical probability of one sound following another sound. For Jelinek's overriding philosophy was essentially ignore the grammar rules and let the data do the talking.
He famously joked that every time he fired a linguist, the performance of the speech recognizer went up.
Yes. And he was right. The brute force statistics of HMMs completely replaced the clever stretching of dynamic time warping and dominated the entire industry for decades.
HMMs got us through the 80s and 90s. They gave us early dictation software and those automated phone trees where we all end up yelling representative into the receiver.
We've all been there.
But by the 2000s, HMMs hit a wall. The error rates just stopped dropping. The source material notes the math was suffering from gradient diminishing and weak temporal correlation. Let's unpack that.
Okay, so to understand gradient diminishing, imagine playing a massive game of telephone. You whisper a complex sentence down a line of 100 people. By the time it reaches the 100th person, the original meaning is completely lost or distorted.
Right.
In machine learning, as an algorithm passes information backward through its layers to learn and correct its errors, which is a process involving mathematical gradients, that signal fades over time. The system literally forgets the context.
Wow. And for speech, where the meaning of a word at the end of a sentence depends entirely on a word spoken 20 seconds earlier at the beginning.
That loss of memory is catastrophic.
Right. So, to get to the highly capable voice assistants you and I rely on today, machines needed an entirely new kind of architecture. And that architecture was deep learning.
Yes.
Moving into the 2010s, we see the rise of deep neural networks, specifically long short-term memory networks, or LSTMs.
LSTMs directly solved that vanishing gradient problem. They are engineered with internal mechanisms called gates that act like a digital notepad.
A digital notepad, okay.
Yeah. These gates decide what information is important enough to keep and what should be thrown away, allowing the network to actively remember events that happened thousands of discrete time steps earlier. That memory allows the AI to maintain the context of a full paragraph.
It also changed how these systems were built from the ground up, right? With the old statistical HMMs, engineers had to manually build an acoustic model, a separate pronunciation dictionary to teach it how words sound, and a massive language model that took up gigabytes of memory just to guess word order.
It was very disjointed.
But deep learning brought us end-to-end models.
A prime example is the LAS model, which stands for Listen, Attend, and Spell. Instead of engineers manually cobbling together 3 different clunky components, an end-to-end model learns everything simultaneously.
That's incredible.
It listens to the acoustic signal, uses an attention mechanism to focus on the most relevant parts of that specific audio snippet, and then directly spells out the transcript. It absorbs the raw audio and the correct text transcription, and it builds its own internal unreadable rules for how to connect the two.
And the results were staggering. In 2017, Microsoft hit a milestone that sounds like pure science fiction. They achieved human parity on the switchboard conversational task.
A massive breakthrough.
They got their deep learning model's error rate down to roughly 4%, which exactly matched the error rate of 4 professional human transcribers working together to double-check each other's work.
Right.
But I want to push back on this term human parity.
Okay, let's hear it.
If a machine matches my error rate in transcribing a conversation, does it actually comprehend the conversation? Or is it more like a giant, incredibly complex pinball machine?
A pinball machine.
Yeah, like the audio goes in, bounces off a million mathematical bumpers, and lands in the exact right text slot, but the machine has zero concept of what a slot even is.
I mean, the pinball machine is a highly accurate way to look at it. It is vital to recognize that the machine does not understand meaning in any biological or cognitive sense. It doesn't know what a dog is or what sadness sounds like.
Right, it's just math.
What these deep neural networks are doing is building incredibly sophisticated topographical maps of sound. They are layering millions of mathematical weights to recognize nonlinear patterns. So it doesn't possess a human mind, but it has mapped the acoustic landscape so perfectly that it can navigate it just as well as we can.
It is mimicking understanding through sheer geometric complexity. But let's pull this technology out of the pristine Microsoft testing labs and put it into the messy, real world.
Let's do it.
Because the stakes change dramatically when you leave the lab. I want to know how this mathematical marvel holds up when the environment gets noisy, highly stressful, or medically vital.
The military applications detailed in the research serve as the ultimate stress test for this tech.
I can imagine.
Take the Eurofighter Typhoon. It utilizes voice commands to actively reduce pilot workload in the cockpit. A pilot flying at supersonic speeds can assign radar targets with 2 quick voice commands instead of looking down and hunting for a physical button on a screen.
That sounds super convenient, but the cockpit of a fighter jet is a violently hostile acoustic environment.
Exactly. When researchers tested these systems in the Swedish JAS-39 Gripen fighter jet, they found that pulling high G loads literally crushed the pilot's lungs, altering their breathing and vocal tract so severely that the recognition accuracy plummeted.
Which totally makes sense. But the source material highlights an amazing detail. A pilot speaking broken English did not negatively impact the system's accuracy at all. Only the physical G-force broke it.
Right.
Wait, so why would a machine care about G-force but completely ignore terrible grammar and a thick accent?
Well, because the deep learning model isn't grading an English exam. It isn't looking for a dictionary perfect pronunciation. It is looking for consistent acoustic patterns. If a pilot consistently says target instead of target, the math still aligns with the model's internal topography. The pattern is reliable.
But G-force physically deforms the human body.
Yes, it changes the physical shape of the vocal tract and the pressure of the air being expelled. The acoustic pattern itself warps unpredictably and the math falls apart.
So it is fundamentally an issue of physical load. And we see that same reliance on the technology to reduce load in healthcare.
Huge impact there.
Following the 2009 ARRA standards that pushed hospitals to adopt electronic health records, speech recognition became a critical lifeline for doctors drowning in paperwork.
Yeah, in radiology, doctors use voice macros. Saying a single short phrase like normal report triggers the software to automatically populate a massive amount of structured medical boilerplate text, saving immense amounts of administrative time.
The underlying theme across these environments is cognitive and physical friction. Whether it is a pilot pulling 5Gs, a radiologist reviewing hundreds of scans, or you standing in your kitchen with your hands completely covered in flour yelling at a smart speaker to set a 10-minute timer.
The technology exists to bypass the physical limits of human hands and eyes.
And for individuals with disabilities, bypassing those physical limits isn't just a kitchen convenience, it's an absolute necessity.
It's life-changing.
The research points out that sufferers of severe repetitive strain injury, or RSI, were actually the urgent early adopters who funded and drove this market in the early days. For someone whose physical disability precludes using a keyboard, voice commands are the only bridge to independence.
It allows hands-free navigation of a digital world, and it powers deaf telephony for real-time captioning. It's also reshaping education, specifically in language learning.
How so?
Modern pronunciation assessment software can listen to a student and grade their speech. But the philosophical focus has shifted. The algorithms are no longer programmed to demand a perfect, standardized native accent. Instead, they assess core intelligibility.
Meaning what, exactly?
The machine asks, can the core sequence of phonemes be mathematically understood? If so, it's correct.
Though the sources make a point to say it's not a magical silver bullet. While dictation software can be a massive help to students with dyslexia who struggle with spelling, the software's inevitable mistakes can actually cause severe frustration.
Oh, absolutely.
For a user with a learning disability, having to stop, grab a mouse, highlight a misheard word, and manually fix it takes significantly more cognitive effort and time than just typing it slowly in the first place.
Which brings us to a critical reality check about the state of the art. Despite hitting that coveted human parity metric in a quiet laboratory, these systems are still incredibly fallible in the wild.
Yeah, they are.
And they contain massive blind spots that make them vulnerable to both innocent, highly annoying mistakes and active malicious attacks.
Let's talk about those blind spots. The standard industry metric here is word error rate, or WER. The research shows that your error rate shoots up astronomically as your vocabulary grows.
Yeah.
Recognizing the digits 0 through 9 is almost mathematically perfect. But ask a system to handle a 100,000-word vocabulary, you might see a 45% error rate. But the most infamous, persistent blind spot in speech recognition is something called the E-set.
The E-set refers to the specific English letters that rhyme with the letter E, B, C, D, G, P, T, V, Z. Historically, and even today, speech recognition systems fail miserably at telling these letters apart.
If you're listening to this right now, I want you to try something. Say the letter B out loud. Now say the letter V. Notice how 90% of the sound actually coming out of your mouth for both letters is just a long, sustained E sound.
Yep.
To a human ear, the tiny pop of your lips at the beginning of B or the vibration of your teeth for V is obvious. We pick up on the context. But why do these massive deep learning models with their long short-term memory and thousands of time steps still fail at something a kindergarten student can do effortlessly?
It comes down to how machines visualize sound. Remember those 10-millisecond slices of audio? The spectrograms.
The flip book.
Exactly. Deep learning still fundamentally relies on plotting volume and frequency over time. Because the letters B and V have nearly identical, incredibly loud vowel sounds attached to them, the sustained E absolutely dominates the data graph.
So the consonant gets a...
Mathematically, the tiny consonant burst at the beginning is treated like a rounding error. The machine's topography for B and V looks nearly identical.
Its absolute reliance on raw math over human intuition is exactly what makes it blind.
And that precise reliance on acoustic math is exactly what modern hackers are weaponizing.
This part is scary.
Because speech recognition is now woven into the fabric of our homes, our cars, and our phones, these mathematical blind spots are severe security risks. We've all experienced the innocent version of this, an accidental trigger where a television commercial says, "Alexa," and suddenly your living room wakes up.
Right.
But researchers have demonstrated active, targeted attacks that are terrifyingly clever.
The artificial sound attacks detailed in the source material blew my mind. Hackers can transmit ultrasound frequencies. These are acoustic waves that are completely inaudible to the human ear.
But not to a machine.
Right. The physical microphone on your smart speaker can still pick them up. The AI intercepts the ultrasound, mathematically translates those frequencies into a valid command, and executes it without you ever hearing a single sound in the room.
It's silent.
They can silently tell your phone to open your calendar, read your messages, or make purchases.
They can also execute attacks by hiding tiny, specifically calculated distortions inside normal audio. To your human ear, it just sounds like a standard pop song playing on the radio.
Just music.
Just music. But to the deep learning neural network, those hidden mathematical distortions overlay perfectly onto the acoustic map for the phrase, "unlock the front door." The machine's incredible mathematical precision is turned against it.
It is a wild, delicate balance between ultimate convenience and invisible vulnerability. We have traveled a massive distance today. From the 16-word IBM shoebox at the 1962 World's Fair, through the timeline-stretching math of dynamic time warping, into the frozen 10-millisecond slices of hidden Markov models, all the way to the deep neural networks that sit in your kitchen today, quietly mapping the topography of your voice.
It really highlights that every single time you use a voice assistant, you are interacting with decades of compounding invisible mathematics.
So, to you, the listener, the next time your device totally misunderstands a word, or infuriatingly confuses a B for a V while you're spelling a password, don't just get mad at it.
Take a break.
Remember the 10-millisecond slices. Remember the deep neural networks working tirelessly behind the scenes, bouncing your audio around a billion mathematical bumpers, desperately trying to decode the fluid, messy reality of human speech into cold, hard data.
It is doing the absolute best it can with the geometry it has.
But before we wrap up, I want to leave you with one final, mind-bending detail from our source material about where this entire field is heading next.
Oh, this is the best part.
In 2018, researchers at the MIT Media Lab announced a prototype device called Alter Ego. It does not use a microphone at all. Instead, it uses medical-grade electrodes placed precisely on your jaw and face to read the neuromuscular signals you generate when you simply subvocalize.
And subvocalization is when you talk to yourself in your head. You don't make a sound, you don't even open your mouth. But your brain still sends tiny electrical signals to your vocal cords and facial muscles preparing to speak the word.
And the Alter Ego device intercepts those electrical signals before they ever become sound.
Right.
The researchers trained a convolutional neural network, which is a type of AI normally used to recognize visual patterns in images, like finding a face in a photograph, to treat those electrical muscle signals like an image. It looks for the visual pattern of the electricity and translates those silent physical signals directly into text.
It's incredible.
Think back to where we started this deep dive. That basic human expectation that speech is a fluid, invisible wave of sound traveling through the air. If a machine can translate the words you merely think about saying by reading the electricity in your face without you ever having to open your mouth, is the ultimate future of teaching machines how to listen actually entirely silent, something to mull over. Until next time.